An acid chloride can be synthesized from a carboxylic acid using thionyl chloride. I'm going to be showing the mechanism of this reaction. Note that if you look at it in the book, there is an error in the mechanism in the book. And I'll explain that as I'm going through the mechanism here. You can optionally add pyridine to the reaction, which would prevent the formation of HCl, and instead you would get pyridinium chloride, which is a weaker acid. So, however, the addition of pyridine is not necessary. Let's talk about the mechanism. So if we look at an acid chloride structure, a carboxylic acid structure. So carboxylic acids have resonance contributors, and there's actually 3, but I'm just going to draw one other one just to show something important about a carboxylic acid. So if we do the allylic lone pair pattern, then we can draw this contributor, which shows that the oxygen on top is actually much more negatively charged than the oxygen on the bottom. And usually if asked, students will point to the oxygen on the bottom being the one that's more nucleophilic, but it's actually the oxygen on the top that's more nucleophilic and negatively charged, and that's seen by the second resonance contributor. So when I attack thionyl chloride, it will actually be the top oxygen that attacks. So let's draw out SOCl2. And the sulfur is very electrophilic. It's attached to all those electronegative atoms. So the nucleophilic oxygen will attack the sulfur. This is possible to do this in 1 step, but the book shows it as 2 steps, so I will go ahead and do the same. So let's draw what we generated. We have this oxygen up here that's negatively charged, and then the sulfur still has 2 chlorines attached. Okay, and then we can go ahead and kick out one of the chlorides. That regenerates the sulfur-oxygen double bond. And now, effectively what we have is a very good leaving group. Instead of the this oxygen up here, we have the entire oxygen, sulfur to chlorine part that's a good leaving group. So we also formed some chloride, and this is where what I draw for a mechanism differs from the Klein book. Klein will use this chloride to deprotonate the hydrogen attached to the positively charged oxygen, and then he'll use another chloride to do a nucleophilic attack. But we've only formed 1 chloride, so we can't use it twice. The pKa of this protonated oxygen is about -7, and the pKa of HCl is about the same, -7. So the proton will basically go back and forth between HCl and then this protonated oxygen. And but once it's attached to the oxygen, instead of doing a deprotonation, what we can do is use chloride as a nucleophile. And it can do a nucleophilic attack on the electrophilic carbon, sending electrons up to the oxygen via resonance. All right, so we showed nucleophilic attack of chloride, and then the chloride is of course a good leaving group, but so is this other leaving group attached. So instead of kicking out chloride, we'll kick this out and we'll form some SO2 gas and some chloride. So we did form some SO2 gas, which will bubble out of solution. And then we also formed some chloride at the end here. So if there wasn't any pyridine around, chloride would be the best base in solution. So it would take this proton. And again, the pKa of both is approximately equivalent. So the product here is an acid chloride. And we also generated some HCl.